Have you ever felt attracted to somebody? Well, because that has a physical explanation, so don't think too far. Stay tuned in this video to understand what I'm talking about. Hello everybody and welcome. Today we're going to be talking about gravitational force. Did you know that any two objects have an attractive force pulling them together? Yes, any two objects in the world have an attractive force pulling them together. Right now, you have an attractive force between you and, say, the computer you're sitting in front of. Well, why don't we feel this force? Well, because it's very, very, very small. Why is it very small? Now we will understand why. So as we said that luckily this force is too small to notice for all objects, but is strong and clear in very large objects. For example, Earth and the Moon, or Earth and the Sun. It is one of the main reasons that the planets stay in orbit. So this gravitational force, it is one of the most important reasons why we stay in orbit. Now, the gravitational force between any two objects can be calculated easily using this law called the universal law of gravity. The force between any two objects, let's call it Fg, which is the gravitational force, it's equal to G multiplied by m1 multiplied by m2 divided by r squared. So F is the force we're looking for. G, it's the constant of universal gravitation, and it's a constant number, 6.673 multiplied by 10 to the power negative 11. So it's a constant number that does not change. Now for m1 and m2, they are the masses of the first and the second object. So for example, if I want to find the force between the moon and Earth, for example, I need the mass of the moon, let's call it m1, and I need the mass of Earth, let's call it m2, okay? And I will also need the distance between them. So r in this case, it's the distance from the center of the moon to the center of Earth, let's call it r. So it's a very simple and straightforward equation. Now the gravitational force two objects exert on each other are equal in magnitude and opposite in direction, because it's an action and it will have a reaction. So every action has a reaction, equal in magnitude and opposite in direction. So if Earth pulls a moon with a certain force, this means that the moon pulls the Earth with the same amount of force but in the opposite direction. We know that the force that Earth pulls down objects with is called the weight, because we introduced weight before. We said that the weight of any object is equal to the mass multiplied by the gravitational acceleration, which is g. Now, the weight is like the gravitational force between any object and Earth. So, where is this taking us? Using this idea, we can derive an equation that calculates g, which is the gravitational acceleration, for any planet, or for example, Earth. So we can say that g, which is the gravitational acceleration, it's equal to g capital, which we introduced before, which is equal to 6.673 multiplied by 10 to the power negative 11. Me here, for example, it's the mass of Earth or any other planet divided by re squared, which is the radius of Earth or any other planet. So if I have the mass and the radius of any planet, we can simply calculate the gravitational acceleration. Now, so this is g. If we multiply it by m, or the mass of the object, now we're back to the general equation that says that Fg is equal to m of Earth, for example, multiplied by m of the object, divided by r squared, or the radius of Earth squared, multiplied by this g capital. So, for example, if this is Earth and a human being is on the surface of Earth, the force between him and the center of Earth, or Earth actually, we can say this is the radius of Earth, and we have the mass of Earth, and we have the mass of the object or the man, etc. It's just simply using this equation again. So what we did is just we took this factor out and we transformed this into a certain number and we called it g. Why did we use it, or why did we transform it into a constant number? Because in our case, for example, Earth, g is constant, mass of the Earth is always constant, and the radius of Earth is always constant. This is just some extra information so we can understand where the constant g came from. So for example, some of you already know that the constant g for the moon, for example, it's equal to 10 over 6 or 9.8 divided by 6. It's 1 over 6 from the gravitational acceleration of Earth. From where did we get that? Simply, we know the radius of the moon and we know the mass of the moon, so we simply calculated the gravitational acceleration on the moon. So it's a straightforward and also easy topic. Now, the equation can be used to calculate the value of g. This means that the gravitational acceleration on any planet depends only on the mass and the radius of this planet. So let's start solving some problems. It says that if an object weighs 100 newtons on Earth's surface, okay, when it's moved to a point 1 Earth radius above the Earth's surface, it will weigh how much? Now, for example, this is the first case. The object is on the surface of Earth. It weighs 100 newtons, okay? Now we moved it to a distance that is equal to the radius of Earth plus the radius of Earth. So what happened is that we just doubled the radius or we doubled the distance between the object and Earth. Now we know that the force that is caused between the object and the Earth, it's simply equal to g multiplied by the mass of Earth multiplied by the mass of the object divided by the radius squared. Now this is the first case. In the other case, or sorry, when the case was this, the force or the weight was equal to 100. It's mentioned in the questions. It's 100 newtons right here. It's shown. Now, in the second case, the force will be equal to g multiplied by the mass of Earth multiplied by the mass of the man divided by the 2 times the radius squared. So what happened here actually, it's that if we want to rewrite the equation, it's g me multiplied by m divided by 2 squared, which is 4r squared. Now, I already know that this whole constant right here, we calculated before, it was equal to 100. So if I want to calculate the force in the second time, it's going to be equal to 100 divided by 4. So the answer is 25. Now, to make things more simple, if we double the distance between the two objects, we reduce the force by 4. Okay, and if we decrease the distance between two objects, for example, by half, we will make the force 4 times larger. Because here the radius, it is squared. So if we play or we change the radius, always keep in mind that changing the radius is always squared. So another example, if the object now is 3 times farther away from Earth, the force will be 9 times smaller. If it was, for example, 4 times away from Earth, it will be 1 over 16 times smaller, etc. So the radius or the distance between the two objects is always squared. Next question. It says that the acceleration due to gravity on the moon's surface is 1/6 of the acceleration due to gravity on Earth's surface. This means that if a person could throw a small object, he can throw it about 2.5 times as high on the moon as on the Earth, or he can throw it 6 times as high, or he can throw it 36 times as high, or an object that has a mass of 1 kilogram on Earth has the mass of 6 kilograms on the moon. Let's look at these choices. Let's start with the first choice, choice A. It says that a person could throw a small object 2 times higher. Well, this is, for example, the moon, and this is, for example, Earth. We have that the gravity here is 1 over 6 of the gravity on Earth. So it's obvious that when somebody throws an object upwards, it has a weight applied on it. In this case, it's going to be equal to mg of the moon, okay? While if somebody throws an object upwards, it will have a weight equal to m multiplied by g of Earth. So this means if the object, or sorry, if the gravity on this planet or on the moon is 1 over 6 of the gravity on Earth, this means that the weight will be 6 times smaller, okay? Because this is equal to g of Earth divided by 6. So the weight of any object on the moon will be 6 times smaller. So if the weight is 6 times smaller, this means that the person can be able to throw an object 6 times as high on the moon as on the Earth. Okay, what about choice D? Why isn't it correct? An object that has a mass of 1 kilogram on Earth has a mass of 6 kilograms on the moon? No, because the mass is always the same and it does not change. So it's obvious and clear that the answer is B. Next question. It says here that the weight of a person on Earth's surface is W. Assume that the radius of the Earth was made twice as great but with the same mass. The weight of the person on that surface would be equal to, well, again, the weight is equal to m multiplied by g. Now, what's happening here is that we doubled the radius of Earth, but we know that g, or the gravity of Earth, is equal to constant multiplied by the mass of Earth divided by the radius of Earth squared. Okay, so what's going to happen to g if we double the radius? Well, let's do it again. G in the second time, it's going to be equal to g multiplied by the mass of Earth divided by 2 times the radius of Earth. Again, it's squared. This means that g will be 4 times smaller from the gravity of Earth. Okay, so if the gravity is 4 times smaller, if we go back to our equation, our weight is going to be m multiplied by g over 4. So this means that our weight will be 4 times smaller. So it's going to be w over 4. Oh yeah, and the answer here, it's shown, it's B. Next question. If the force of gravity suddenly ceased to exist, the satellite that is orbiting the Earth would move away from the Earth along a line that is tangent to the original orbit, move away from Earth along a radial line from the Earth's center, or will it move away from the Earth along a curved arc path, or will it fall to the Earth along a radial line from the Earth's center? So when it happens, actually it's more related to the circular motion equations or questions, so we can say that it will move away along a tangential path, because we know that, for example, this is Earth, this is the object that is orbiting around the Earth, it will have a tangential velocity. So let's say what's holding it in place, it's the gravity between it and between Earth and this object. So if this gravity is to be deleted, this means that the object will go in a tangential direction. Questions 5 and 6 are related. Planet X and Y shown below each have a uniform density. Okay, why are we mentioning uniform density? Because not all planets have uniform density. Actually, I'm not sure that any planet has any uniform density. Because, for example, Earth, the deeper you go into the Earth, the higher the density. And if the density changes, the whole force equation won't give the same answers. Now, Planet X has twice the radius of Planet Y. The center of the planets are distance d apart from each other, and the object of small mass is located at any of the 4 points shown, A, B, C, and D. Question 5 says, at which point is the gravitational force exerted on the object by planet Y the least? So he's asking about planet Y. Which points, A, B, C, or D, is the force exerted by Y the least? Well, actually, it's obvious that it's point A. Why is it point A? Because it's farthest from planet Y. The farther we are from planet Y, the weaker the force is. Now, at which point is the gravitational force exerted on the object by planet X greatest? Actually, again, I think it's the same answer. It's A, because it's closer to the center of this planet right here. So the closer we are, the smaller the distance, the greater the force. So in both cases, the answer is A. Stay tuned. In the next videos, we will be introducing more topics. We will be talking about Kepler's law. See you then.